In today's lecture, we're going to go through writing functions in assembler, and before we actually get to the details of how we can actually implement a function, we need to discuss a piece of memory that you have probably interacted with many times while programming, though perhaps implicitly, and that is the stack, and how to actually directly add and remove data from the stack. So we're going to cover those two aspects. The one is really a necessary condition for the other. So up until now, we've mostly ignored the stack while programming in assembler, and we've basically relied solely on just using the data and the BSS segment to store our variables. But obviously, as we start writing more complicated programs, we're going to start needing more memory than just fixed allocation will provide us. Obviously, you could always allocate a lot of memory, but there are capacity limits on how much you can really do. But most programs of any sufficient level of complexity require some kind of degree of variable size allocation. And for that, we're going to start using the stack. Now, obviously, there's the other type of more classical dynamic allocated memory, which is the heap. We're not going to be discussing heap memory yet. We'll still get to that, most likely in the next lecture. However, we're focusing at the moment on the stack. So what you see here is just a bit of a recap of the Linux process model, where we have our text segment, which is our code, our data segment, which is where we've been kind of storing some of our variables, and at the top of this process model is the stack. Now, what's a little interesting about the way the stack works is that this lower address by the text segment corresponds to address 0. Now, obviously, as I mentioned in one of the earlier lectures, if you actually test this in practice, there's a little bit of stack randomization, so these addresses won't be exactly 0, but for the purposes of understanding what's going on, you can assume that the bottom of this text segment starts at 0, and this top of the stack actually starts at the location of 47 ones. Okay, it's a very large address. What is interesting, however, about the stack is that when we start working with it, you'll see that we actually grow the stack in a downward fashion. So as I add more to the stack, I end up growing downwards, which is not the way in which you may normally expect to actually add more information. You might try and grow an address space, but in fact, when we allocate more memory from a stack, we actually minus. But we'll go through that in more explicit detail shortly. So let's try and give ourselves a little bit more context about how the stack works and places that it pops up in our normal everyday programs before we get to the assembler side of things. So consider the following intentionally inefficient implementation of the Fibonacci function. Now, obviously, we know with the Fibonacci sequence, we basically have a situation where we have 1, 1, 2, 3, and then the next element is the sum of the two previous ones, so 5, 8, and so on. Now, there's a couple of ways you can implement it. What I'm going to show you obviously here is just a simple recursive approach, which is not the most efficient, but it will demonstrate what I want to demonstrate quite effectively. So let's also assume that I don't know that I can actually just get the Fibonacci value using an explicit equation. If you're currently enrolled for WW 285, you'll actually be able to derive this because obviously Fibonacci is a second order non-homogeneous recurrence relation. But that's an aside. For the moment, let's just actually look at the Fibonacci implementation here. So we have a function that will take in an input n, which will return a specific Fibonacci number, so the fifth Fibonacci number, for example, and it will return that number as an integer as well. Code's pretty straightforward. We have our base case. If n is less than 2, we're just going to return 1, so that corresponds for those two cases there. And if that's not the case, we're not at a base, we need to do our kind of recursive step. So I'm going to calculate the Fibonacci number for n minus 1. So basically, if I was calculating this, I want to figure out what this value is. I'm going to set that to be fib m minus 1. And then I'm going to calculate fib n minus 2 and set this variable fib m2 to be that value. Now, obviously, you're all familiar with this example, so that's really not too much of a concern. Then we're going to return the sum of the two. Okay, so straightforward example. But even though this is a really simple program, it's very easy to actually cause your program to crash if you have a value for n that is too large. Now, the question is, why is this happening? Why do we get this crash? Or in this case, the specific type of crash is referred to as a stack overflow. It's not just a website name, it's a thing that actually happens in your program when you allocate so much memory onto the stack that you breach the official stack boundary in the Linux or any process model for that matter. that the operating system has allowed you, and once you've breached that actual boundary, you get a stack overflow. You've overflowed past the capacity that you were actually allowed to use. But why is this happening? What aspect of this code was adding information onto the stack? So let's try and work this out. There are really two causes for what is happening in this specific example. Though in some sense they're very much related, the distinction between this first and the second cause that I'll go through is that this first one is a little bit more obvious. The second one is a little bit more subtle. It requires you to have a little bit more of a thorough understanding of the way in which functions are actually called in a program. So let's look at the simpler case. Say I want to try and figure out how much memory my program is actually going to end up taking. Well, in the case of our simple Fibonacci function, you should know from COS 212 that this naive Fibonacci algorithm has a space complexity of order n. And if we consider that it's order n, let's actually see how much space is used if I try and calculate Fibonacci 10 million. Now, there's a little bit of an extra bit of information that I'm not going to include in this calculation, which is the subtle point that I was referring to earlier. But for the moment, let's just ride with this example. So I had two variables in that bit of code. I had this fib1 or fibm1 and this fibm2. So I have two 32-bit values. Remember, in 64-bit Linux, an int is 32 bits. Or rather 4 bytes. Okay, so with that in mind, this program itself is going to require 2 times 4 bytes because we had two variables. And if I'm actually calling this recursive function, I need to go 10,000 deep to get down to the base of that recursive expanded tree. Just to get down to the root node, I'm going to need 10,000 of these variables, rather 10 million of these variables. So we can do a little bit simple math, and we'll actually see that in the case of calling Fibonacci of 10 million, I actually require, just catering for those two variables, 67 megs worth of space. Now you might think, well, that's not that much. I mean, sometimes programs work with video files and large pieces of data, so why is this an issue? Well, actually, the stack is quite limited by default, and generally this limit is not changed that frequently. And in most Linux distros, you actually work with a stack that is between 8 and 16 megabytes. Okay, so the idea is that your stack shouldn't actually generally be very large. You can change this in C++, for example. Some languages it's a little harder to do than others. It's largely not so much a language thing specifically. It's more of an operating system request that you need to request that the process model allows for a larger stack. Not so much a language thing as I just mentioned. But which distro you have will dictate what the default is. So if you're, for example, on Arch, Linux, or Gentoo, I believe you get 16 megs, and distros like Ubuntu only give you 8. You can Google how to change it. It's not necessary, however, to change it. You actually see some people that compete in programming competitions actually artificially set the stack limit to be as high as the system will allow them, so that they can exploit deeper recursive calls. But regardless, at some point you're going to hit this limit. So say we want to avoid this stack overflow, maybe I can get around it by not storing variables. Okay, I mean, obviously that was in C++ code, but maybe I did something, for example, where I didn't explicitly store these two variables and I just returned the sum. Maybe I could avoid somehow saving those values to actual extra variables. Maybe I could reduce the necessity to have those two extra integers. So even if we could, say it was possible to remove it, there's still one aspect of the code that we cannot avoid in terms of stack utilization. And that is that we need to actually store the return address when we make a function call onto the stack. And this return address will always occupy space. Even if the function itself occupies no space, the return address will require space. So even if it was possible that there are no stack items, we would still have to push this return address. We would always have at least that one stack item, even if we removed those local variables. So let's maybe just see what would happen without actually explicitly manipulating the stack, just to try and shore up your understanding of why we have this notion of a return address. Say I'm executing a bunch of code. So these are my lines, like 1, 2, 3, and so forth. And over here, I call a function. Okay, let's call this function foo. And I jump into my function foo. Just say it's an int, for example. And I have a bunch of lines here. I execute my function. Now the question is, when I get to the end of this function and I make use of the return keyword, how does my program know that I should go from this specific location in the function back to the location one after the function I just called? I mean, it's something we take for granted, really. We call a function, we know we'll be returned back to the location where I made the function call, but how is that happening? Now, what's actually happening is that when I make a call to a function like foo, I save the address, so let's just say indicate with label, of the next instruction after that function call. And specifically, I save it onto the stack. Now, the stack will be accessible to this function foo during its whole run. So when I actually get to this return, I can just look at the corresponding location on the stack and recover that return address. So it's basically I've gotten back that label. And once I've gotten back that label, I know where I need to jump back to in my main program, and then I can continue executing as normal. Now, if I have multiple function calls, so say for example, I have a situation where I have foo calling another function, say foo2. And obviously this can kind of repeat indefinitely where I have functions calling other functions. So how does this work? Well, it's just an extension of the same idea. Whenever I call a specific function, I save the address one after that function, so the next instruction. So I end up having on my stack basically a bunch of return addresses. So you can think of having like a return address 1, return address 2, return address 3, and once I'm at the end of this outer function, I basically jump back to this location, remove it from the stack, and now my new top of my stack I can use to return back to the earlier level of function. So basically I can just keep on adding the return addresses to the stack, and I always make sure I use the address that is at the top of the stack in terms of which one I jump back to, because that's the most recent function that called the current function. Now, it's a little bit more complicated than just stacking these actual return addresses on top of each other, because there's a little bit of extra machinery at play on the stack. But in terms of conceptual thought, you can think of it as just having a stack of all of the return addresses. Okay, that's in essence what's happening. Now, there's a lot more complexity that comes into play with doing this directly in assembler. Specifically, our stack actually grows downwards instead of upwards, so that's one thing to deal with. And two, there's a thing called a stack frame, which we need to kind of actually set up. And that's because we have another issue that can come up with building functions, is that if I have some local variables that are stored on the stack and I call a function, what do I do with those local variables that were on the stack from the higher order functions? Say I have a main and it has some stack-based variables and it calls the function foo. What do I do with those original stack-based variables? How do I make sure they're preserved? So that's why we need to build what's called a stack frame, but we'll get there shortly. Now that we've seen how we can actually, in some sense, break the stack by causing a stack overflow, let's actually try and discuss how we can utilize the stack directly. So the first point to just recall or restate from a little bit earlier is that the stack will start at the location 7 followed by many f's, which is basically just 47 ones, unless there's some amount of stack randomization in place. And actually that's likely to be the case, but you can assume that that's roughly where the stack is going to start. Now the second point that we should always keep in mind is that the RSP register, which we actually mentioned when we discussed registers but haven't used very much, actually stores the stack pointer. So this will point to the current location of the stack. And if nothing has been added to the stack, our stack pointer, assuming there's no stack randomization, will simply contain the top of this stack, which will just be the 47 ones. So in our process model, basically, it's going to be this situation where it's going to be pointing to the top of our stack. Okay, with our heap being over here. Now, the way we interact with our stack is relatively simple once you get used to it, but there's a couple of subtleties that I think we should always try and keep in mind. Now, there are pretty much two distinct ways of interacting with the stack. The simplest, and probably the one that you're most likely to encounter if you look at tutorials and things like that, is to use what's referred to as a push or a pop instruction. Makes sense because a push and a pop operation is what you've commonly used when working with a stack data structure in general. And we can interact with the process model stack using push and pop, and we're going to go through that now. But there's an alternative approach where we more directly alter the stack pointer rather than using the push and pops. Both approaches are fine. Some are better in some situations than others. So let's go through the push and the pop instruction variant first. So the push instruction decrements the RSP register and stores the value being pushed at this address. So remember, the stack grows downwards. So if I want to increase the amount of space in the stack, I actually have to subtract from RSP. I have to subtract some amount from RSP, and that's why when I perform a push operator, I actually decrement the RSP register and store the value being pushed at that address. The pop instruction on the other side will place the value that's currently in the operand at the top of the stack, and it will increment the RSP pointer. So if I'm popping, I'm actually reducing the size of the stack, and that's why I'm actually going to increment the RSP pointer. Now with x86 64-bit instructions, you should actually always push and pop 8 bytes at a time. There's a good reason for this, which is related to stack alignment, which I'll get to as we proceed with how to write functions in assembler. You cannot actually, in 64-bit mode at least, push and pop 32-bit registers directly. It's disabled. You can, however, push and pop 16-bit registers or words. Okay, so that's a point just to keep in mind that direct 4-bit push and pops are not enabled in 64-bit mode. So if you find some example code that's written for 32-bit, they may use instructions like push EAX. This instruction, however, will not work in 64-bit mode. You can only push and pop the 64-bit registers or actually the 16-bit registers when you're in 64-bit mode. So let's look at a kind of visualized example of pushing and popping onto the stack. So here we have our stack with a couple of addresses just indicated. So we have the top of the stack over here, with this being the initial value of RSP. It's pointing at the top of the stack, and I've just indicated this by this red line over here. So let's push a couple of values onto the stack and then pop them and see what happens to the stack. So the first little chunk here, I'm going to move the value of 74 into the RAX register, and then I'm going to call push on the RX register. Now, as mentioned before, this will decrement the RSP pointer or the stack pointer, and then it will load the value in to the stack that was in the register. So my stack pointer moves down by 8 bytes because I'm actually pushing a 64-bit register, so it needs to move by 8 bytes. And you can actually see this on the left because we went from a 0 to an E8. So I went down by 8. And then I load in my specific value. Great, simple enough. Let's try and keep this chain going. So let's say increment RAX, so now it would have the value 75, and I call push RAX again. Same procedure. My RSP pointer gets decremented. So again, we went from E8 to E0 because we changed by 8 bytes. The stack pointer is now at this location, and we simply load in, stack pointer is at this location, and we simply load in the value of 75. We can repeat this one last time, where we increment RAX, push RAX, and we end up moving the stack pointer and loading in the value of 76. What happens if we execute a pop instruction? Well, if I run pop RAX, it will increment RA, or the stack pointer rather. You see this red line now. So it will increment it, and it will extract the value that was where this X is now, and store it in RAX. So in this case, RAX would contain the value of 76. If I call pop again, I will simply be moving the stack pointer again, and the value that was at this now X that I'm highlighting will be stored in RX. So in this case, this RX is going to contain the value of 75, whereas this one had the value of 76. Okay. Now, something that you should actually be mindful of here is that you may be under the impression, at least, that when I move the stack pointer, so when I move the stack pointer up from this E0 to EF, when I made this move over here, I may have deleted what was stored here. The truth is that what is ever in that location on the stack is simply left untouched. It's not zeroed out or anything like that. It's simply left as if. We're just moving the pointer, but whatever was actually stored in the location underneath it is simply left there. It is not zeroed out. Okay, so that's something I think is worth thinking about, because you might think by doing this that I'm introducing, for example, a 0, I'm blanking it out, but I'm actually not. I'm just moving the pointer. I'm not doing any extra steps by zeroing out the old data at all. Now, obviously, we're going to be working with the stack quite a bit when we write functions and just in general. So it's good that you can actually analyze what's going on in your stack. So I've just included this little chunk that I want you to just play with at home of how to actually inspect the stack pointer as you actually do this manipulation. And you can actually use this to actually check the elements in the stack by just using offsets from the current stack pointer. So make sure you can actually analyze the stack. It's going to be very important when you start doing recursive functions in assembler to make sure you understand what is actually happening with that stack. Now, stack space is often reserved for local variables by, instead of using push operators, but rather by subtracting the size of the needed space from the stack pointer. So say I know I need 56 bytes worth of stack space for my variables, I could actually directly subtract that number from RSP. Now, there's actually a thing that will come up when we get to functions shortly, and that is that you want your stack pointer to be on a multiple of 16. This is to make sure that certain SIMD instructions, so that's the instructions where I perform multiple calculations in one instruction, work correctly. It's something that is necessary to be fully C++ compliant, but we'll get to that shortly. So there is a bit of a constraint on what's a good amount to subtract from RSP, but before we get to functions, in essence, you could subtract as much space as you wanted. If I needed 517 bytes, I can simply go subtract 517 from RSP, and that in essence has allocated me that much space on the stack. The question now is that I've allocated myself the space, how do I access that data or store into that data? So in this example, I've simply subtracted 16, and I intend on storing values for 2 quad words. So each quad word took 8 bytes, so I needed to subtract 16 to cater for the 2. So the first thing I'm going to do here is I want to save what I'm going to call my first quad word. So I'm going to have this value 123, for example, and I'm going to save it into RSP plus 8. Okay. Now this plus 8 might seem a bit weird, but we'll clarify that shortly. And then I'm going to save my second variable in this case, which is 24, and I'm going to save this into the location at RSP. Now, the reason this works is that here's my stack, and here is my current RSP after I've subtracted 16. Now, if I'm just going to draw a line to indicate 8-byte divides. If I'm at this location RSP and I add 8 and I store a value like this 123, in essence, I'm loading into this spot here. So say this was like location 0, this was location 8. When I simply go RSP plus 8, I will now load into this location. Now, normally this is empty at the top, so I say this is the top of the top of my process model memory, at least. So I'm going to call this my first variable, and in principle you could say your first is closer to the stack pointer or not, that choice is yours, but this is what I'm going to be using as my first stack-based variable. And my second stack-based variable, instead of having an offset of 8, I'm going to have an offset of 0, and that would load the value over there. So this command is in principle the same as me simply going RSP plus 0. Okay. Rather just use RSP, but in principle, that's what's actually happening. Now, this can lead to certain issues because I have the intention here of saving two 64-bit values. So what would end up happening if, instead of actually using the correct offset, if I did something like this, if I had move RSP plus 424, what would actually end up happening and then is that I would actually end up interacting with the other register unintentionally. So that's something to, or the other bit of memory. So that's something to keep in mind. So let's look at what actually happens in this example. So again, I have my stack addresses on the left and my original stack pointer is at the top of my stack. First thing I'm going to do is I'm going to subtract 16 from RSP, and this frees up my space on the stack. Now, just like what happened before when I subtracted from, or sorry, when I performed a pop operation and the stack pointer moved back up, and I didn't clear anything in the process, the same thing occurs here, that these locations are not any set value. They're just whatever was in memory. So they're not 0, they're whatever was in memory. So that's something to keep in mind. You cannot assume that they're just 0. Now if I load in 123 at using the offset of 8, I'll end up loading this 123 as my first variable. And in the same vein, if I want to load my first variable, I simply use this move RSP and I have my 24, and this will load it into this location for me. Okay. Now, remembering these offsets, while in this case was kind of straightforward because we only had two variables, or two stack-based variables, if I had many, it would become potentially cumbersome. It's for me to always keep track of where they are. For example, say I had 6 variables. Now I always need to remember, okay, my variable that is storing, say, my sum is at offset 16. But now I have that extra cognitive load to keep in mind. So what I recommend you do, and what is common practice, is we utilize what's called the EQU pseudo-op. It's simply called a pseudo-op because it's not a true operand. It's basically a little bit of syntactic sugar that assembler gives you to kind of substitute values. So in essence, instead of me always using 8 trying to get access to my first variable, I simply include this pseudo-op, which I label first, followed by EQU for equal, and then the value that it's meant to store. So you can think of this as basically being a constant in your system that you can call up for different purposes. So in this case, I simply say RSP plus first, and it will always add the 8. Same thing implies, or is relevant for the second variable here, that I can simply go EQ0, and in this case I'm going to call it second, and it will simply substitute the value 0 in for me. So that makes it quite a lot easier to kind of scale up your program, such that if I have many variables, what I'm actually working with becomes a little bit easier for me to manage. The next thing you have to ask yourself is, okay, well, we know how to allocate space on the stack. I mean, we simply were able to do that by subtracting from the stack. So how do we actually delete these variables after we have used them? Well, you could perform a sequence of pops, but that would require that your pop sizes match up to the full allocation that you've made. And it also means that you might have many pops. If, say, for example, you subtracted 57 bytes, you may have to pop quite a few times, and then you have some awkward little bit of leftover space to even deal with. However, the answer is actually quite easy. All we have to do is we just add to the stack pointer. So in this example, we had subtracted 16 from RSP, and instead of subtracting 16, we're simply going to add 16, and this will end up deleting what we had higher up. Now again, this delete is a kind of symbolic delete, because what has happened is, say this was my 2 stack-based variables. When I executed this add, I moved the stack pointer such that it now points over here. So assume each of these chunks is 8 bits. Okay, so 8 bytes. Now, what has happened here is I've only moved the stack pointer. What was in these locations, so in this case it would have been the 123 and the 24, are still there. But for all intents and purposes, we treat it as if the memory has been deallocated, okay, because we're not actively working with that space. Okay, so in the same way in which when we allocate a new space, we don't clear it out. When we delete the space, we leave it as it was. We don't kind of clean things up for the next person. We just blank it out. Now, there are some kind of important considerations with this. If you have a lot of sensitive data and you're somehow worried that your stack can be interpreted by a function deeper inside, it might be prudent to be careful with what you actually wipe and don't wipe from memory, but that's a whole different kettle of fish and actually something you shouldn't be worrying about when just coding the normal assembler. There's a field dedicated to avoiding those kind of attacks. I've just realized actually that there's a slight error on some of these operands, which I'll update in the slides. You'll notice here that I don't actually indicate the size of the corresponding move because we have an immediate value here, and this is simply a memory location. The question is how much data am I actually moving. This instruction will actually not assemble. It needs to be move keyword RSP plus first and then the value. So in essence, you just need to add this keyword. So that would occur over here, and actually it would have occurred in all of these locations, which I'll just update in the slides. But while I think about it, I should just actually mention that we do actually need those size specifiers. Now we can start actually getting into some of the nitty-gritty about actually constructing functions, and we'll see as we develop to the point of actually writing sufficiently complex functions why we needed that stack-based information. So let's assume that we've already loaded in our parameters for our function. Now I'll explain what this loading in of parameters actually means shortly, but for the moment let's assume we've loaded in our parameters. So say your function took 6 parameters and now you want to call it, so assume that's done. How do we actually call said function in assembler? The way in which we do it is simply using the instruction call followed by a label, and this label should be some kind of appropriate address in your code or text segment. Now actually in principle you could specify an address in your data segment and your assembler will not complain, however your program is more than likely going to crash. So in general that label should be some corresponding text segment, and there's a couple of things to keep in mind here. The first is that the function will actually always return some kind of value, and the return value will exist in one of two registers. It will either return a value in RAX if it is some kind of integer-based return value. Now, interestingly enough, the integer-based in this case would include things like pointers, and so more complicated objects generally actually come back via a pointer-like structure. Or in the case of a floating point calculation, the return value will be stored in XMM0. Now don't worry too much about that for the moment, we'll cover that in the next lecture, but just so you can refer back to these slides once we've covered floating points, it's worth including this here. So how does this call function actually work? What is it doing? Well, we already discussed earlier how we have to push onto the stack a return address when I actually call a function, so that deeper function knows where to return to once it's completed its execution. So the way in which we can actually emulate this call with native, or with more simple instructions rather, is as follows. I have a label for the instruction or the location in memory just after where I'm about to make my call, okay? Or in this case, I'm going to jump. Now what I first do is I push that address onto the stack. So basically I'm saving my return address onto the stack, and then I'm simply going to jump to my function location. Now obviously I have to do a little bit of extra trickery to get back from that function. However, because of pushing on this next instruction address, I know I have saved and stored securely on my stack the location I need to return to once I'm finished doing my execution. So in essence, this call function is doing exactly this triplet over here. So these two instructions followed by a label. So how do we actually return from our function? Well, luckily for us, there's a shortcut way, but I still feel it's good to understand what the more complicated approach to doing the same thing is. Now, the simple way is to just use the instruction ret. Now, note you don't have a return value with ret. Ret is a zero operand instruction. And in effect, what it does is it will pop an address off the stack and branch to it. So basically, it pops whatever's on the top of the stack, and it uses that as the address for which it's going to perform the next execution at. So if I didn't have access to this ret instruction, what I would have to do is I'd first have to pop off my stack into some 64-bit register. Remember, all labels in our case with 64-bit assembler will be long, so they take up a whole 64 bits. And I can choose any register name here, or any 64-bit register name. I'm just choosing RDA for simplicity. So I'm going to pop onto RDI, and then I'm going to jump to RDI. So basically, I'm going to jump to the location that RDI contains. And if I had performed a call, then I obviously have this next instruction nice and saved, or that address of next instruction nice and saved onto my stack. And that's where I'll end up returning to once I perform that jump. Now, in practice, you generally don't end up having to actually use these primitive operands. You simply use call and ret, but it's very important that you understand what's actually happening underneath how they work. Specifically because if you're aware that call actually alters the stack, you can actually have a better understanding of what we need to do to perform stack alignment later on and things like that. So you know why the stack pointer suddenly changed when you made a call instruction. Now, the next aspect we need to discuss about functions is function parameters. I discussed earlier in the example that we assumed we had loaded those parameters in. So if we haven't loaded them in, how do we go about doing it? Well, this is where assembly can become a little bit tricky, because the manner in which we have to actually build functions, and in particular how we build functions to work with C++ and C programs, is very specific to what type of bit system you're in. So if you're in a 32-bit system or a 64-bit system, and there's a fundamental distinction between Windows and Linux. So everything about these functions is in relation to Linux. I'm going to briefly mention the distinction when we talk about Windows, but for the purposes of this course, it's good enough to understand that Windows is different than Linux, but I'm not going to ask you to, for example, implement something specifically to work for Windows. I will assume we always are implementing in the context of 64-bit Linux. So in 32-bit Linux, just so we have kind of a bit of historical background, is all parameters were actually pushed onto the stack. So if I had 6 parameters I wanted to pass to my function, I would push all of them onto the stack. Luckily for us, because we have a lot more registers at our disposal in 64-bit assembler, some of these parameters actually pass directly through via registers. Now in Linux and in macOS, we pass integers and address parameters using the following 6 registers. So corresponding to the first parameter all the way through the 6 is RDI, RSI, RDX, RCX, R8, and R9. So parameter 1, 2, 3, 4, 5, and 6. If we have more than 6 parameters we wish to pass, we have to push those onto the stack. But by and large, the majority of your programs will require less than 6 registers or 6 parameters. The same thing actually applies if I want to pass floating point parameters through, in that I can actually make use of pre-designed registers. So the first 6 floating point parameters can actually be passed using XMM0 through XMM5. Again, we'll get to floating point parameters later, but this is so you can refer back to it later. Windows does things a little bit differently, even in the 64-bit case, and that is that it uses registers RCX, RDX, R8, and R9 for the first integer or address parameters, and everything after that gets pushed onto the stack, plus a little bit of extra trickery in that there's a little bit of what's referred to as stack padding. So there's a designed bit of empty space before the real variable is actually present on the stack. Okay, there's specific reasons that that's done in terms of inducing some kind of level of compatibility between 64-bit and 32-bit Windows. But again, our focus is very much here in that we care about 64-bit Linux programming. Now, if you happen to actually need to push parameters onto the stack, so say you're in old 32-bit Linux, or you have more than 6 parameters in the case of 64-bit Linux, all parameters are pushed onto the stack in reverse order. So that's the key word here, that they're pushed onto the stack in reverse order. So if that comes up, keep that in mind. There's one thing that's also worth mentioning is that some functions that you will actually call, say for example, directly in C++, like printf, have what's referred to as a variable number of parameters for certain functions. So I mean, obviously printf, you pass through a string and you pass through as many corresponding extra parameters as you want. In particular, you could have an arbitrary number of floating point parameters. So the way in which functions like that are dealt with is that we have to set rax to be the number of parameters we wish to pass to it. It's a little bit of a special case situation, but you'll see that come up quite frequently. But I make explicit mention of it because you'll see as we go forward, we will actually start making use of some C functions directly, such as printf and scanf. And in that context, you will often see us setting rax to 0 because we have no floating point parameters. So it's just so that you understand why we're making that decision. Now, this little table you see at the bottom is a table that I'll always give you in a test kind of scenario, or you're allowed to use in a test scenario. And this is referred to as the system ABI. So it's called a system abstract binary interface. And this is different depending on what system you're working with. Remember, 64-bit Linux is a little bit different than 64-bit Windows, and 64-bit Linux is different than 32-bit Linux. So what you see in this table is the ABI for 64-bit Linux. And in some sense, this is kind of the rules of play to actually write functions that will work between C++ and assembler, and C and assembler. And this table is quite useful in the sense that you'll see that it indicates which is the first parameter, the second parameter, third, fourth, fifth, and sixth, so you can remember that. But it also kind of illustrates that there are certain rules to using some registers. And this is a place where students can kind of come unstuck. Now, there's this notion of what's referred to as a function preserve, or a register that is preserved across function calls. Now, what this means is that if I load something, in this case, into rax, so in essence what happens is that if I load something into rax and I call a function, that function is under no obligation to preserve what was in rax before it was called. It is free rein to use that register and not reinstate its value. So that register value is not preserved across function calls. So I can't use it as a safe space to store anything when I make a function call, because that function could alter it. There are some registers that are in fact preserved. The first is RBX. The RBX often has a specific use as a base pointer, which I'll illustrate what that is shortly. But the function is obliged to always reinstate RBX if it changed it. If it set it to a specific value, it has to set it back to its original value before it returns. So the same thing applies with RSP and RBP. Again, those have very specific use cases. However, what is quite useful is that there is this agreement with registers R12 to R15, which are called callee save registers, is that the function is obliged to reinstate the value. So say I have some value stored in R12, say I have the value 57, and I call a function. When that function returns, R12 should still have that value in it. So that function is obliged to reinstate it. Now, that doesn't mean that the function can't use that register. It just means if it does decide to use it, it has to fix the value in it such that it is what it was before the function was called. And we'll see actually as we go forward that a lot of times when you write functions, particularly functions that call other functions, that you need to save certain bits of important information either onto the stack or into call save registers. The downside of using call save registers, however, is that the deeper function, if it does use those registers, has to also make sure it reinstates them. So you kind of need to be consistent with how you treat it. But this is kind of the contract that all functions must follow to comply with the system ABI in 64-bit Linux. And this is vital if we're going to interact with C and C++ functions. So say I'm calling a C or C++ function, calling my own functions even, or if C and C++ functions are going to call my functions that I've implemented in assembler. So let's implement a couple of simple functions before we get to more complicated ones. So here we have a nice function which simply returns the larger of two values. So you'll see I've just indicated here in this comment what the prototype for this function would be in C++ or C. So the first thing just to keep in mind here is that it's a max function, so it's going to return the larger of the two inputs. All variables here are of type long, and in 64-bit Linux, a long is 8 bytes or 64 bits. Okay, so that's something I want to make sure that you remember, that a long is always 64 bits, and int is 32. And a pointer, for example, for an address is always a long, which is always 64 bits. Okay, so that aside, here I have my max function, so I have a label called max, and what I'm going to do is pretty simple. I basically need to gain access to the parameters. So remember, RDI is the first parameter and RSI is the second parameter. So I want to make sure I return the larger of the two. So I'm going to load RDI into RAX. Then I'm going to compare RAX with RSI. And if RAX is in fact less than RSI, so that basically means if parameter 1 was less than parameter 2, I'm rather going to set RAX to be parameter 2. And then I'm going to call return. Now remember earlier that RAX contains my return variable, and I loaded the larger of the two variables into RAX. So when I call return, the person that's made use of my function knows that the value that they are looking for will now exist in RAX. So how do I call this function? So this is an implementation of a function. Before I actually get to how I call it, this type of function is what's referred to as a leaf function. We call it a leaf function because it doesn't call any other functions. Now that term is going to come up kind of frequently when we distinguish between a leaf function and a non-leaf function. But this is a good example of what's called a leaf function. It doesn't call any other functions. So how do I call the function? It's relatively straightforward. I basically just have to load up my parameters. So I'm going to load up RDI with 123. And then I'm going to load up RSI with a value of 742. Then I'm going to call max, and RAX will now contain the larger of the two. So in this case, it's going to contain 742. Okay, so very straightforward kind of approach to load up the variables. It gets a little bit more complicated if I need to load past the 6 and I need to start using the stack. This is very much in line with how we are performing system calls in your pracs, for example, where you have a situation where you have to load, say, 5 registers. It is because you're loading in specific values. Okay, you're basically loading up the parameters. Now, something else that you may have encountered, depending on how you chose to implement things, is that when I made a call, for example, to a system call, any register that was not necessarily going to be preserved across that system call could have been changed. So it's just something to keep in mind. Now, the next step is a little bit more complicated, and it's something that is very important if you want your programs to interact with C and C++, which is what we are going to do in this course. So your pracs and assignments, you have to make sure you follow this. And it's this notion of enforcing stack alignment, okay? And the notion of stack alignment is present to ensure that certain other instructions, that other functions that you may call, work correctly. So it's kind of an additional rule of play when actually implementing real-world functions. Now, both Linux and Windows in 64-bit mode require the maintenance of the stack on a 16-byte boundary during the main part of a function. So basically that means that at any point, if I'm going to call another function or an instruction, I need to actually ensure that my stack is on a multiple of 16. Now, at the moment, you won't immediately have access to the instructions that make that vital. You'll see that will come up as soon as we do the summed instructions. But you don't know necessarily what type of instructions a function you're about to call is going to use. For example, you don't necessarily know the implementation of printf or scanf. And because they may make use of those specialized instructions, you're obliged to ensure that you maintain this 16-byte boundary, or rather that the address of the boundary is always on a multiple of 16. So it's something that we have to actually always do. It feels somewhat arbitrary, but it's necessary to ensure that functions that we can call always work effectively. Now, there's a small little thing I should actually mention, is that we mentioned earlier that there's a little bit of stack randomization. Regardless of where that stack randomization occurs, you will always start on a multiple of 16. So you don't need to worry about trying to shift it to be initially on a multiple of 16. Regardless of what stack randomization may occur, you'll always start on a multiple of 16. Now, the reason as well that this 16-byte alignment is required is that in order for some of the subsequent instructions to actually execute correctly, some of the SIMD instructions, they require the data that they're going to use to actually be on a 16-byte boundary. So that's where it comes from. So as I mentioned, this is related specifically to the SIMD instructions. So these SSE instructions and the more recent version of it, which is the ABX instructions. We'll get through to those in more detail later on, but actually a lot of modern advancement in terms of high performance compute of CPUs, other than just increasing thread counts and core counts, actually came from these AVX instructions. The one disparity perhaps there is that Intel provides AVX 512 instructions, which a lot of people don't feel are that relevant. The AVX 256 is more than sufficient for most things, and we'll go through AVX 128 and 256 in the floating point lecture. Cool. Now, one thing that I should mention actually is that even our simplest function that we devised earlier actually doesn't meet this criteria. It doesn't actually preserve the 16-byte boundary alignment, and that's because when I make a function call, I have pushed the return address onto the stack. So let's assume, for example, that the current address was a multiple of 8, multiple of 16, and then I simply add one address. Now I've added 8 to it. It can no longer be a multiple of 16. So we need to actually fix that situation. So the way in which this is generally done is actually by using a push instruction. Specifically, we push RBP, and this establishes, or reestablishes rather, the 16-byte boundary that was for a very short period of time botched by the function call. And this is obviously because the function call pushes only 8 bytes onto the stack. Now, in essence, you don't have to actually use RBP to achieve this. You could just push any 8-byte entity onto the stack and it would work out fine. But there's a specific reason that we use RBP in practice, and RBP is often referred to as the base pointer, and we'll see where that comes into play now when we actually build and destroy stack frames. Cool. One other thing that I think one should always keep in mind is that following that kind of reestablishing of the 16-byte boundary is that any subsequent use of stack space should also ensure that we end up with a multiple of 16. So say, for example, I only need 4 bytes of space on my stack. Instead of me subtracting 4, I have to subtract the closest 16-byte value to the one I'm subtracting that is larger than it. So say, for example, if I only have 4 bytes that I need to allocate, then I actually need to subtract 16 to ensure I'm on a 16-byte boundary. Say I needed to actually only use 27 bytes, then I would actually need to subtract 32, and the same thing proceeds the whole way up. You round up to the nearest 16. And we'll see this with all the examples pretty much going forward, that we always kind of we either allocate precisely if it works out, but most often we end up over allocating to ensure we get that 16-byte alignment. So let's look at an example. This is an example where we're actually linking into C. So, and you'll see actually from assignment /prac 4 onwards, we'll be making use of C functions. So you'll have access to printf and scanf. So you don't have to worry too much about those system calls going forward. So it's obviously good to know how they all work, but we're able to use the C versions from assignment 4 onwards. So in this example, I'm going to be making use of the function printf from C, and to use it, you'll see that there's a couple of structural pieces at play here. So this is basically just printing out hello world, And you'll see my entry point is main because I'm going to link this using GCC. So these first two lines are what's referred to as our stack frame construction. These bottom two lines are referred to as our stack frame destruction, okay, or deconstruction rather. Now, we haven't explained the purpose of these two instructions as of yet. However, we know that we want to push onto the stack to actually restore the 16-byte boundary. Now remember, what actually happens here is underscore start calls main, which means even in main, we need to actually reestablish that 16-byte boundary alignment. So with that in mind, we have to push a 64-bit register onto the stack. So here we have this push RBP. And before we return, so that we are guaranteed that what's on the top of the stack is actually a return address, we have to pop off what was on the stack. So in this case, I'm going to just simply pop back into RBP. But the biggest takeaway at this point, at least, is that we want to remove what's on top of the stack, this like artificial RBP, such that when I call return, it will return to the correct location. Now RBP has a more specific meaning, which I'll get to shortly. So that's the first part of this example. We have the stack frame setup and destruction. And if you actually write any function pretty much going forward, I recommend that you simply start with writing the stack frame setup and destruction kind of as your first step in writing the functions. There are situations where you don't explicitly need a stack frame setup and destruction in the context of a leaf node function. However, there's nothing preventing you from just always using the stack frame setup and destruction. So I'd recommend doing that as like your go-to approach. So I want to make use of printf. Now, as you'll recall, printf basically takes a string and then it takes an arbitrary number of parameters, and the number of parameters you use will actually, generally speaking, depend on how many special characters you've indicated inside this printf. So how many entities you've said that you're going to print. So for our example, we don't have any. We're simply going to be printing out a singular message. So I'm going to load in my character string. So I'm just going to load MSG into RDI. It's basically the first parameter. Remember, RDI is the first parameter of a function. I'm then also going to move 0 into RAX. That's because I'm indicating I'm using 0 floating point parameters. Again, it's kind of a feature of printf. And then I'm going to call printf. And this will print my screen for me. Or sorry, print hello world to my terminal for me. And then I can proceed from there. Now, what I'm doing over here is I'm simply loading 0 into RAX because that will actually be our return value for main. Now, if you recall how C++ works, actually, is that 0 means that you had a correct termination of your program. So we actually want to ensure that if everything went fine, we actually load 0 into RAX and return. Because this printf could have also changed RAX. It could have set it to something else. It could have been a return value from printf. Okay, so now that we've done that, so let's spend a little bit more time on this actual stack frame. Now the stack frame is largely used by the GDB debugger to allow us to trace backwards through the stack and inspect calls made in a process. So say for example you got a bug or something went wrong in your code 5 function calls deep. Okay, how do I actually go back and inspect the local variables of the different functions? So let's say I have my code and I jump to another function, and at some point I jump to another function, and then eventually I have encountered some issue over here. And now I'm trying to debug what's gone wrong. Now, it's easy enough for me to inspect with GDB the stack local variables to this stack frame, the one I'm currently in. However, how do I actually figure out what the local variables are doing in that stack frame and that stack frame? That becomes a little bit harder, and that's actually why we build and destroy these stack frames, because what ends up happening here is by using this combination of pushing the base pointer onto the stack, saving our current stack pointer into RBP, and then once we're finished with the code, we basically reinstate the stack pointer to be what the base pointer was. So basically we undo any subtractions we may perform or pushes and pops we may perform. We basically undo it and we pop RBP So we basically load back the base pointer of the calling function in essence, and then we return to it. By doing this setup and destruction, we actually end up building a linked list of all the stack frames. Now it sounds a little bit odd, but you'll see now in the example I'll show you that it's quite an elegant way of making it easy to traverse to different stack frames for different function levels. And you'll see how that works now. Now, all functions that are non-leaf functions, now remember a non-leaf function is a function that doesn't call, a non-leaf function is a function that calls another function. A leaf function is one that doesn't call any functions. Now, all non-leaf functions must have a stack frame setup and destruction to conform to the ABI for proper interfacing with C and C++. Okay, so it's a requirement to effectively work with C and C++. But it also gives us this useful ability in GDB, even if we're not actually interfacing with C and C++. So it's kind of good in two ways. So let's look at this premise of building this linked list. Let's actually just run through this notion of calling functions within functions within functions and see what would happen to RBP, RSP, and my actual stack. Now, for the demonstration of this example, we're actually assuming I am not storing any local variables just to make it simpler. So I want you to think about where they would go in this context, but we can demonstrate this linked list construct this way quite easily. So we're now in our base function, and RBP will start up as 0 by default. And RSP will contain our current stack pointer because it always starts at our current top. So you can think of this basically being in _start. That would be the most reflective of this in practice. Now, if I call a function, so I'm going to call this function level 1. So for the purposes of this example, what's happening is the base function is calling L1, L1 is calling L2, L2 is calling L3, and L3 is calling L4. So when I call L1 from my base function, I perform my stack frame setup and destruction. Well, in this case, we're only interested in the setup part because we haven't destroyed anything. So I'm going to set RBP to be the current RSP. So remember, this is basically that line over there. And RSP will now be my new stack pointer. Now, this may have changed during the course of this run. I may have allocated more space for something. I may have subtracted to put some local variables. But what's important as well is what's happened to my stack. So on my stack, the first thing that was added was the return address to the base. So that happened simply by calling call. So call L1 would have induced that. And then I saved over here my RBP. This happened from the push instruction over here. So that saved the base pointer. So basically in this case, it's just saved what was stored over here. So it just saved the old base pointer. Now what happens if we proceed in the same fashion? First thing is that my new base pointer becomes the old RSP, so my old stack pointer. And then we have now our new stack pointer that could have been changed by allocations and things like that. But let's see how the actual stack changed. Well, the first two entries that we had before remain untouched. But we add the return address to L1, so we could get back. And then from that push RBP instruction, we end up adding the stack pointer onto our stack. Now we can proceed in the same vein again and again and again as deep as we go. But let's consider what happens if we're at level 4. So there's one over here. And we now want to debug. And I want to be able to traverse the different layers. Now we can actually quite quickly identify this linked list. Okay, so you'll see here at the top of my stack, though it has the lower address, it's still at the what we would call at the top of the stack. I have stack pointer 2. Now what this actually points to is that location over there. It points to where the next stack pointer is. This stack pointer 1 actually points to the location where stack pointer 0 is. And the stack pointer 0 actually ends up pointing to this 0 element. So you can kind of think of this as the end of the linked list. I hit my null element. Now what this means is if I want to debug and I know I want to go back one layer, all that has to happen is I have to traverse my linked list one layer. So I go from say layer 2 to layer 1, and now from this current location, I can use my offsets to gain access to all the variables local to that stack space. So I can get all of the variables that are local to L3 without any issues. And I can repeat this process no matter how deep my functions are. So it's a little bit odd that it builds this linked list in the procedure, but it gives us the ability to actually debug the code very effectively. And you'll see obviously there's a cost associated with this. I'm adding more things to my stack, but given that we had to add that extra 8 bytes anyway to preserve 16-byte alignments, it's kind of a perfect solution because we're able to solve a problem that we had, i.e. that we ended up changing that stack base point or the stack pointer to not be on a multiple of 16 because it was on 8. We managed to change it to be on a multiple of the 16, and we used that extra space on the stack for something useful. In this case, that useful thing was this linked list, which gives us the ability to perform traversal through the different stack frames, which means we can debug in this context. And it means GDB will work when we have multiple levels of function calls. Now, the next thing we need to answer is, what do we do if I need local variable space? I mean, I've discussed now being able to access the local variable space, but how do I actually access it? Well, we already know how to do this in essence because we were able to manipulate the stack in a function oblivious fashion where we were just working with the stack directly. But now we can actually do this at the function level. So if we require space for local variables, all we have to do is we just need to subtract an amount from our stack pointer. Now, the subtraction, once again, must always maintain a 16-byte boundary so that we stay compliant to the ABI. So say, for example, I only need a single quad word as a local variable. I just need one. Maybe it's called sum, for example. And that's all I technically need. I only, in principle, have to subtract 8 because that's all I need. But to maintain my compliance, I should actually subtract 16 bytes. So even though I'm only going to be using 8, I always need to subtract that multiple of 16. So here we basically do our stack frame setup, and then I just subtract what I need for my local variables. And if we allocate local variables, we must use this destruction where I reinstate RBP to RSP. And basically what this does is it undoes any type of subtraction I've done because I'm reinstating the copy I made over here. The same thing is actually applied if I added extra pushes inside this function. This instruction will reinstate it to what the original stack pointer was, which is quite convenient, at least for us. So that's why we have that instruction over there. So something to keep in mind here is just popping is not necessarily going to work because we're actually going to not effectively reinstate the stack pointer then. We need to make sure that we give or set the stack pointer back so it's correct by the time the high level function is actually accessing it again. And now remember that these local variables are very much isolated to each of the functions because, let's go back to this example, you'll see here that I have space. So I have my stack pointer, but I will always allocate space basically between. So I'd allocate extra space here and extra space here. Obviously, this is not reflected in the address space for my local variables. Okay, so now we know how we can subtract the space necessary to gain access to those variables. It's pretty much as we did with normal stacks before we even worked with functions. Now, one thing I should mention is that this combo of two instructions to destroy the stack frame is, in some sense, I would almost recommend you type it as a bit of a habit in the beginning so you can understand what is happening and you're conscious of what's happening with these registers. But there is shorthand to do it, which is just the leave instruction, and in essence it performs exactly these two operands. They are equivalent in practice, so one's not worse or better than the other. They basically do the same thing. The latter is just a little bit more transparent in terms of what's happening. So let's look at another example. So we're going to write a function called printmax and call it from our main. So here we have our main function again. So again, we're assuming we're linking in GCC. I'm going to set up my stack frame, and then I'm going to destroy my stack frame. Again, you can just start writing your programs like that. You don't even need to think too much about it. You just know you need to start a function with that. Then I'm going to make a call to print max, which I have yet to go through. So we're going to still implement it, but in essence, print max in this case is going to take 2 longs and print them to the screen. So I'm going to load my first parameter, which is into RDI. I'm going to load my second parameter into RSI, and then I'm going to call my print max. Then I'm going to load 0 into RX because I intend to return 0 to show that everything ended correctly in this function. So let's implement the print max function. That's where we're going to actually have to start using the stack a little bit more. So this is just the prototype for our print max. It doesn't return anything, but it takes in 2 longs. So the first thing I'm going to do is I'm going to set up some EQs using the sudo op, so it makes it easier to access my local variables. So I'm going to be using one for A, one for B, and one for max. In this example, we could have actually gotten away with not using as many, but it's still good for demonstrative purposes. So I've decided I'm going to have 3 local variables, and each of them are going to be data quad. So in principle, this would require 24 bytes. Okay, so 3 quad words. However, we want to make sure that we are still on a 16-byte boundary. So instead of subtracting 24, I'm going to subtract 32. So we'll see in my function that once again I set up my stack frame, and the destruction will be later on in this function. But because I want to store local variables, I'm going to subtract 32 from RSP. Okay, so I basically made space for 32 bytes of data, though I only intend on using 24 of them. I'm going to save a copy of my first parameter into A, so A on the stack. Then I'm going to save my second parameter, RSI, into B on the stack. And then lastly, I'm going to save RDI into max on the stack. Now, obviously, that max is not correct yet, but we'll see, we'll swap that around if it's wrong shortly. So to deal with the fact that max is not necessarily the maximum of A and B yet, we're going to just use a simple jump. Could have done this as well with a conditional move, but for the sake of diversity, let's do it in a slightly different way. I'm going to compare RSI and RDI, so I'm basically comparing A and B. If I'm in a situation where I find that B is actually not greater than A, I'm going to end up skipping the move because it means that RDI is actually already the larger of the two, so my statement over here was correct. If, however, RSI is in fact greater, I'm going to execute this command, and in essence it's just simply going to set max equal to RSI, which in this case means I'm going to set max equal to B. Again, could have been done with a conditional move. So let's go down to the next segment. So this is basically the skip label. So I would have jumped to this had I triggered this conditional jump, but I will still get to it even if I don't trigger it. I just simply will not have executed this extra move. Now, you'll see something in this slide that's maybe a little bit different. You'll see that I've linked a data segment with a text segment. It's actually possible in assembler to write text segment, data segment, text segment, data segment as many times as you want. It won't change where the information is stored in the Linux process model. By that I mean that your data segment and your text segment are still separate, but I can interleave them as I write it in assembler. I just have to always reinstate what type or what segment specifically is this line meant to go into, but I can interchange it, and you'll see this is done in a couple of examples. So here in this little very tiny data segment, we basically simply have a format string, which indicates that I'm going to be printing 3 long decimals. So in this case, this basically just means it's longs. And I'm going to basically be saying the max of the first value, the second value is equal to whatever the max happens to be. Okay, so how do we actually execute that print? Well, we want to use the printf function. So the first parameter is that format string. I simply load the format string's address into RDI because that's the first parameter. And again, if you don't remember, check that table. It will tell you what's the first, second, third, fourth, all the way up to sixth. Then I'm going to load the first actual integer parameter. So it will be the second parameter to the function. So I'm going to load A into RSI. Then I'm going to load B into RDX. I'm going to load max into RCX, because remember this is going to be the first, the second, and third values. So this would correspond to the second parameter, the third parameter, and the fourth parameter of the function printf. Then I'm going to set Rx to be 0, because remember printf requires that I tell it how many floating point parameters it's going to receive, and then I call printf. Okay, then I'm simply going to destroy my stack frame and return. Okay, now you'll note here that I haven't set the return value to 0. So what in essence is actually going to happen here is the return value of this function is going to actually be whatever printf set rax to. Now this isn't an issue because we decided that this print max is going to return void. But what is interesting with assembler is regardless of what I actually intend to have as the return type, it will always still be able to set rax. So in this case, the rax value will be whatever printf returned, though we kind of made the high level decision that we're not going to care about what the return type is, or the return value is rather. Now there's something that's a little bit subtle, and it's an issue that is easily avoidable if you follow one specific rule or you change the way you access local variables slightly. So I want you to maybe pause the video here and think of if you can encounter a problem where the way in which you access local variables could be destabilized during the course of a function somehow. Okay, so once you've thought about that for a minute, I'm going to now say what the issue really is. The issue comes in is if anything is pushed or even popped from the stack, our offsets will suddenly not be correct because we were using RSP plus a specific value. But now if somebody performs a push operator, it changes what RSP is, and the same with pop, which means my offsets will now suddenly be wrong. So how do I actually fix that? Well, as I said, there are two ways. One is kind of a fix, the other is a rule of thumb, really. The fix is to, instead of using RSP and plus, we actually rather use RBP and minus. Now, the reason that happens is that RSP is basically at the limit of what we've expanded our stack to. So I'm always moving back up in that direction. So that's why I'll always be adding to it. However, RBP is what's saved as the base pointer, so it will be before I've allocated the extra space. So that's why I'll need to be subtracting from it. I need to move downwards in the address space if I use RBP. Now, you'll see different programmers use one or the other approach. Now, you can use both. I actually rather recommend that you stick with using RSP for the sake of all our assessments and things like that. It's a bit clearer, but you will see the RBP approach being used. Now, the workaround or rule of thumb, such that you can still just use the RSP plus approach, is you just simply don't use push and pops other than the ones you needed for the stack frame setup and destruction. And in essence, there's no reason to use push and pops if you can just use subtract. I mean, we could always do the subtract up front and know how much space we needed. We don't need to worry too much about the push and pops, but it is something to keep in mind that if you just use RSP plus and during the course of your code you decide to push something onto the stack, your offsets are suddenly not necessarily going to be correct anymore.